All right, let's talk about something that sounds way more intimidating than it actually is. Dependency injection in Go. We're going to break this whole thing down and show you how it's really the secret to writing code that's cleaner, way easier to test, and just more professional.
So, have you ever been in this situation? You write some Go code, it works great, but then you go to write a test for it, or maybe you need to change one tiny thing, and suddenly the whole house of cards comes tumbling down. It's a really common frustration, and it has a habit of sneaking up on you.
And it almost always starts with something that seems totally harmless. You've got a function, it needs to log a message, so you just drop in a fmt.printf. Easy, right? It works. But, and this is the crucial part, by hard-coding that print statement, you've secretly fused your logic directly to the console. Now you can't easily check what it's actually printing in a test.
And this is where dependency injection, or DI for short, comes in to save the day. I promise, even though it has this super formal, kind of scary name, the idea behind it is incredibly simple. It's all about breaking those rigid bonds in your code.
I love this quote I saw on Reddit because it just cuts right through all the technical jargon. It says, "Dependency injection is just a fancy way to say that your objects takes in dependencies instead of initializing them itself." That's it. That's the whole magic trick. Instead of your code building what it needs on the inside, you just give it what it needs from the outside.
Okay, think about it like this. Your phone needs power, right? It's a dependency. But your phone doesn't have a miniature power plant built inside of it. I mean, that would be crazy, and you'd be stuck with only one way to charge it. Instead, it has a standard port, like a USB-C port. It just says, hey, I need power through this specific kind of hole, and you can plug in any charger that fits. That's all dependency injection is. It's giving your code a standard port for its needs.
All right, enough with the analogies. Let's see what this actually looks like in some real Go code. We're going to take that simple greeting function we were talking about, and we're going to fix it.
So on the left, you can see our original function. It's tightly coupled. It calls fmt.printf directly inside itself. It's totally locked to the console. Now look at the improved version on the right, the loosely coupled one. The function signature is different. See how it now accepts an io.writer as an argument? That's our standard port. We are now injecting the dependency. We're telling it where to write the output.
So what did that one little change actually get us? Well, a whole lot. First, our code is now testable. In a test, we can just pass in a little memory buffer and check exactly what got written. Perfect. Second, it's reusable. We can use the exact same function to write to the console or file or even a web request. And third, we've achieved what's called separation of concerns. Our function's only job now is to create the greeting. Where that greeting goes is somebody else's problem. That is real power from a tiny change.
Now, this might seem like a pretty small victory for one tiny function, but this principle, this one idea, is literally the foundation for building clean, scalable, and professional Go applications. Let's zoom out and look at the big picture.
What we've just done is an example of a huge concept in software engineering called inversion of control. You see, normally, our function controlled its dependency. It created it all by itself. With DI, we invert that control. We let something on the outside, like our main function or a test, be the boss and decide which dependency gets used.
Without this idea, we're living in a world of tight coupling. Just think of it like all the parts of your code are welded together with superglue. If you want to test just one little piece, you have to drag all the other pieces it's stuck to along with it. It's messy, it's fragile, and it breaks easily.
But with DI, we get to this beautiful state of loose coupling. Our components are now more like Lego bricks or appliances you plug into a wall. They connect through standard interfaces, plugs and sockets. You can easily swap one piece for another without needing to rewire your entire house.
So, at the end of the day, this isn't just some academic exercise. This is how you build big applications that can actually last and grow. Your code becomes explicit. The function signature is like an honest contract that says exactly what it needs to do its job. Your ability to test things goes through the roof, and as your app gets bigger, adding a new shared dependency like a database connection becomes a clean and simple process instead of a total nightmare.
Okay, so theory is great, but how does this all play out in the real world? This is usually where the conversation turns to frameworks. But with Go, the story is a little bit different.
If you ask a lot of experienced Go developers, they'll tell you that the most Go-like or idiomatic way to do DI is to, well, just do it yourself, manually. You create all your services and dependencies in your main.go file, and you just pass them down. It's simple, it's explicit, there's no magic going on, and for a huge number of projects, it's absolutely the best choice. But
What happens when your project gets really, really big? I'm talking hundreds of different services, all depending on each other. Well, suddenly, your main.go file can start to look like this. A tangled web of constructors, where changing one little thing forces you to refactor dozens of other lines. This is the point where wiring everything up by hand can become a major headache.
And that is the exact problem that DI frameworks were built to solve. They don't do the injection for you. You still have to write your code to accept dependencies. What they do is automate that tedious, error-prone process of building the whole dependency graph for you.
Now, in the Go world, there are basically two main flavors. You've got compile time tools like Google's Wire, which actually generates plain Go code for you. The big win here is there's zero performance hit at runtime, and any errors are caught when you compile. On the other side, you've got runtime tools like Uber's Dig and Fricks. These use reflection, which gives you more flexibility, but you might not discover an error until you actually run the application.
Now, with all this power, it's really easy to get carried away. So we have to ask an equally important question. When is this the wrong tool for the job? When should you not use dependency injection?
There are a few big mistakes to watch out for. First, just don't over-engineer. If you're building a simple command line tool, you probably don't need all this. Second, avoid making interfaces for absolutely everything just because you can. A good rule of thumb in Go is to only introduce an interface when you actually have a second implementation or you really need it for a test. And finally, always remember why you're doing this. The goal is cleaner, more testable code, not just to say you're following some fancy design pattern.
Okay, let's do a super quick final recap. What is it? Just passing your dependencies in instead of making them inside. Why use it? Because you want code that's testable, flexible, and maintainable. And how should you use it? Start by doing it manually. It's the simplest way in Go. Only even think about reaching for a framework when you really start to feel the pain of a massive, complex project.
And that's dependency injection in Go. It's a really simple idea, but it has these huge, powerful consequences for how you structure your code. It's about moving from components that are glued together to components that just plug together. So, the question to ask yourself on your next project is how can you use this to untangle your code? Thanks for watching.